Alright everyone, this video is about a geometric series and what a geometric series is, and more importantly, proving whether or not a geometric series converges or diverges. That's the key. Okay, so the first lesson was about sequences. Sequence is a list of numbers generated by a mathematical rule. A series is where you sum the terms of the sequence together. Now we're going to learn about specific types of series, the first one being geometric. Here is an example of a geometric series. Now what makes this geometric and what does that mean for it to be geometric? It just means that to get from one term to the next, one term to the next, all we're doing is multiplying by a common ratio. And you can see in this problem, we're multiplying by 2. So as long as that's the rule for the generation of the series, you're multiplying by a common ratio, that means the series is geometric. And when it's geometric, we can do a lot of things with it. So in general, it'll look like this. So in this case, this one looks like this. It's 2 to the, in this case, we'll go n minus 1, starting at 1 to infinity. And when you start plugging in, you get the above series. So yeah, this is geometric. They're always going to look like this. Basically, you're going to see kind of an exponential situation going on where you'll have a base to a power. That's what geometrics always tend to look like. So let's put it in general. In general, you'll often see it look like this. N equals 1 to infinity. Sometimes you'll have a coefficient. In this previous problem, we did not. But the trick will be right here. You'll have r to the power of k or n. So we'll stick with n. That's the format. So if you were to plug in 1, the first term would be a times r. If you plugged in 2, the next term would be a times r squared. If you plugged in 3, the next term would be a times r cubed, on and on and on. And you can see that these terms, to get from one to the next, all you're doing is multiplying times r, times a common ratio. And then, by the way, just like integrals, one of the ways to think about an infinite series like this, you could factor an a out of every single term. So r plus r squared plus r cubed, on and on and on. And then we could rewrite this as a times the sum from n equals 1 to infinity of r to the n. So in other words, just like with integrals, coefficients can be moved out of infinite series or any series as long as they're a coefficient that goes to every term. So sometimes you'll see it written like this, sometimes you'll see it written like this. Okay, let's look at an example of a geometric. And let's see the types of questions I will be asking. So if I gave you this geometric series, 0 to infinity, notice I'm starting this one at 0. That's going to start to happen fairly often. Bam, like that. Okay, so this is geometric. And the question is, does this one converge or diverge? That's where we're going to start. So one thing you can do, you could begin writing out the terms of the series. So if you plug in 0, you get 2 times 1/3 to the 0, which is 1. So you get 2 plus. If you plug in 1, you get 2/3. If you plug in 2, you get times a third, 2/9. If you plug in 3, you get 2/27. And on and on and on. Okay, so the first thing to always consider when we are looking at a series and asking whether it converges or diverges, does it pass the test for divergence? Or I should say, does it not get eliminated by the test for divergence? And you can see that, no, this is getting closer and closer to 0. So we can't immediately rule out that it diverges. It could either converge or diverge, so we have to do another test. And this isn't really a test, it's more of a, do you know the properties of a geometric? And here's what you need to know to determine if this in fact does converge or diverge. All you have to do is look at the r value. So in this problem, r is 1/3. And geometrics have a very, very, very important rule you must know. As long as the r value is between -1 and 1, the series converges. So as long as you get an r value between -1 and 1, the series will converge. If it's negative, it's going to actually alternate. We talked about that in class, one of the classes. You'll go to 0, but it'll alternate back and forth between positives and negatives. But that one, in fact, it does converge. So in this case, we have an r value that is between -1 and 1. So immediately you can say this series converges. And then you would just say, because the series is geometric, with r equal to 1/3, which is less than 1. That's a pretty good answer. You're kind of putting everything together. You're saying that it converges. You're saying why you know it converges, what kind of test are you using. In this case, you're saying because you know it's geometric, and then you're stating the condition that needs to be met. In this case, it's the fact that r is equal to 1/3, which is less than 1. So this would be a complete problem that I would want you to be able to do. Now, I will show you this in ClassPly someday, but we can actually find what this series converges to. That is the same as saying, what is the sum of the series? So remember, we have to get used to both notations. Sum of the series is the same as what does the series converge to? And there's a formula for this. In class, I will prove the formula for you. On this video, I will not, because I'm trying to keep them relatively short. So the formula looks like this. To find the sum of an infinite series, you take the first term and you divide it by 1 minus the ratio. In other words, it kind of looks like this. It is, let me make sure I use the right notation. That's fine. A sub 1 or a sub 0, you just got to know that that means the first term over 1 minus r. So for the above series, if I asked you to find what it converges to, aka the sum, you would say the sum is equal to the first term, which is 2, divided by 1 minus the ratio. So you could leave it like that, or you can simplify 2 over 2/3, which is equal to 3. So multiply by the reciprocal, you get 3. And if you were to sit here and actually add them up and find partial sums, you'd approach 3. We're not going to do that because it's not a crucial point. Instead, these are the two big things. You need to know how to show that a series converges if it's geometric, and you need to be able to find the sum if it is in fact geometric. So geometrics are huge. They're going to pop up for the rest of this 2 months. You have to be aware of when a series is geometric. Am I multiplying by a common ratio to get the next term? And if it is, you need to know that it converges if r is less than 1, or between -1 and 1. And then you need to be able to find the sum by using the formula. Those are kind of the biggest pieces to this. Okay, let's do another example then. Next example, let's do series from n equals, we'll go 0 again, to infinity of 5 -2/3 to the n. And the question is, does this converge or diverge? And if it does converge, can you find what it converges to? And that means if you ever hear that phrase, like find what it converges to, chances are it's geometric, because we're not going to be able to find what it converges to often. Really, we're only going to be able to do that when we have a geometric series or something called the Taylor series. Other than that, we're usually just going to be able to say converges or diverges and be done with it. But in this case, since I'm asking what does it converge to, it's a good indicator that it's probably geometric. And yeah, if you're not sure what you're doing, you can always try and expand out the series. I'm going to keep telling you that. So let's just say I don't know what's going on. Let's plug in 0. You get 5. Let's plug in 1. You get -10/3. Let's plug in 2. That becomes positive, and you're squaring this. So it'd be 5 times 4, which is 20 over 9. And then you plug in the next one, you get minus. So plug in, that was 0, 1, 2. Plug in 3, you get a 40 up top, and it's negative, over, you get a 27 in the bottom. And now it may be helpful to see what's going on. Well, am I multiplying by a common ratio? Yeah, you're multiplying by 2/3. And in fact, you're multiplying by -2/3. So -2/3 times -2/3 times -2/3. So this is geometric, with r equal to -2/3. Which, one of the ways we can write it too, because you're like, well, wait, this is less than 1. I mean, I guess you could say it's between -1 and 1, or you could say that the absolute value of r is less than 1. It's another way to say it. Therefore, this series converges. And then in that case, let's find the sum. So the sum, aka what this infinite series converges to, would be the first term, so 5, divided by 1 minus, now you have to be careful with the negative, since it's r is negative, it's a double negative here. So you're going to have 5 over 1 plus 2/3. And then you could simplify or just leave it there. And if you're ever unsure of your answer, try finding a fourth partial sum. If you find the fourth partial sum, you should get an answer very similar to your infinite sum. So that's a quick check you can always do if you have the time to do so and you think something's going wrong. All right, a couple more. Just real quick, if we go back to the very first series, this one that I started us with, what does this one do? Well, it's geometric, but look, r is greater than 1, therefore this one diverges, which should make sense. It also fails the test for divergence, or I should say it gets eliminated by the test for divergence, because look, this limit as we go to infinity is not 0, it's infinity. It's just you keep adding bigger and bigger terms. So that's a case where it's pretty obvious. You could almost do this one two ways. You could either show that it diverges by the test for divergence, or you could say it diverges because it's geometric with r greater than 1. You're going to find that sometimes there are 3 or 4 different tests you can use to prove convergence or divergence. It's going to be a big deal coming up. Okay, so 2 tricks that I want to talk about. So doesn't seem so bad, but sometimes you're going to have to be clever about certain things. So let's start this one at 1, and let's go 4n plus 1 over 5 to the n. That's one tricky series, and here's another one. 1 over 5 to the n equals 0 to infinity. Okay, so geometric's not too hard to deal with. You just have to recognize it's geometric, and sometimes you may have to realize I can rewrite it a certain way. So look at this. Let's say you forget these tricks. You can always expand it out. If you forget the trick, just start writing out terms and then find the first term and see if there's a ratio that's less than 1. So that's always what you can do. However, we can be a little more clever and realize, oh, when I have an exponent like this in the top, I can write this as 4 to the n times 4 over 5 to the n. I'm going to be lazy a lot in this class, by the way, and not write the subscripts and superscript on the sigmas. Just, it's okay. Well, maybe I shouldn't be lazy. But if I do it in class, forgive me, okay? So look at this. I now have this infinite series, and I can rewrite it as 4 times 4 over 5 to the n. And now it looks more like the form we're happy with. We see our coefficient in front. We see our ratio to the nth power. So our first term, when I plug in 1, would be 16/5. My ratio is what is inside of the parentheses. It's 4/5. So using these 2 pieces of information, first, I know r is less than 1. Therefore, it converges because this is geometric. And on top of that, I also know that I can find the sum, which would be the first term, which would be 16/5 over 1 minus the ratio, which is 4/5, which this one actually simplifies kind of nicely. 16/5 over 1 minus 4/5 is 1/5. So it looks like it's just 16. So if you were to find some partial sums, you should get 16 as an answer. Yeah. All right, second one. Like, well, wait, this kind of looks geometric, except the 1 doesn't have an nth power. Does that change anything? Well, not really, because think about it. If it's 1 and there's no power, can't you just write it as 1 to the nth power? Because 1 to anything is still 1. So this is kind of a trick. When you see a 1, you can think of it as 1 to the nth. And then really, that's just the same as 1/5 to the n. And that's also geometric. With r less than 1, this would converge also. Okay, so just little things like that. But if you forget these little tricks, expand it out. Expand out the series. You're going to hear me say that all semester. Expand out the series if you are confused. And a lot of times that will really clear things up, in my opinion. All right, that's it then. Not too much of geometrics. You just got to keep adding this stuff on. Okay, we are adding on a lot of important little tidbits that we have to make sense of when we put it all together. All right, that's it.